Okay, chemistry time. Today we're talking about periodic, let's call this one periodic law. I think in the past I've called it the periodic table. I think the periodic law gets more to the point of what we're actually doing, which is discussing the idea, that is the trends, the patterns that we see in the periodic table. The periodic table is named this because of the patterns that are in it. Something that has a period is something that has a cyclical nature. The moon has a period. That means that the moon cycles from, well, it starts out, we could say it starts out, it's been, so well, I'm just going to put new as the first one. And then, waxing crescent, waxing quarter, waxing gibbous, and then the full moon. And these should be, yeah. And then it wanes again. And have I done this the right direction? I don't know. Don't at me. This is not really the point of this class. I probably should know. It's my job. But don't at me. I think this is right. So there's a periodicity to the moon. The moon phases cycle. There's a pattern to it. There's a name of a There's a name of a kind of document called a periodical, which is issued on a pattern. An example of a periodical is the Crawford Clipper and the Harrison Sun, which every Wednesday gets put in my mailbox. There's a pattern to it. That's what periodic means. So the periodic law is describing the trends in the periodic table of the elements. We already know some trends. If I draw these as the different blocks of the periodic table, how could we label these that tells us that there's a pattern to it? What's this one?
Non-metals.
No. What's this one? As blocks.
Light metals. 1 and 2.
Okay, they are groups 1 and 2, yeah. And they are light metals, and they are metals. Those things are all true, except for hydrogen isn't most of those things. But as a block, what did we label the block? What is the outermost shell of electrons of these are in what shape?
Valence.
Valence is the word, but in what shape?
For the clovers.
No, you're on the right track, though. It's not for the close. No.
S.
S is what I'm looking for, yes. Which is a spherical shell. What about these in the middle here? Or down in the middle? D. These? P. And these ones down here? F. And so this is periodic in the sense that if we are going down the list of elements in order of atomic number, starting with 1, hydrogen, then on to number 2, helium, hydrogen, helium. If we start with 1 and then go to 2, we get this pattern of S, P, S, S, P, 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 etc., which is related to 1s1, 1s2, 2s2, 2p6. You see there's a pattern. That's the way we were able to do our electron configurations from the last chapters, because there's a pattern to it. And that pattern makes it periodic, which is why we call it the periodic table. Now, as was correctly pointed out, is that the only pattern here? No, if we go down that same list, we go through not just blocks. So one way that the periodic table is periodic is through blocks. I'm going to erase helium and hydrogen, erase these, get back to my little blank template of periodic table here. Now, if we again start with hydrogen, helium, lithium, beryllium, etc., but instead of looking at the blocks, instead of looking at the shape of the valence orbital, now we're looking at the kind of thing it is. Well, hydrogen, the gas, helium's a gas, lithium's a metal, beryllium's a metal, then we have carbon, that's not even right. This is my job. Boron, then carbon, then nitrogen, then oxygen. I've kind of run out of room. I wish this guy was a little bit smaller. Oh man, I really did a bad job of that. Oh no. There we go.
Fluorine and then neon.
Fluorine and then neon. So we have this pattern of starting kind of, in the first part we kind of have this somewhat metallic behaving element. Hydrogen is not a metal, but in some conditions when it's under extreme high pressure or extreme low temperature, it does behave as a metal. Helium, which behaves exclusively as an inert substance, usually almost always a gas. And then we have the cycle again of metal, metal, metal-ish. What do we call it when it's almost a metal? You remember from physical science? A metalloid, non-metal, gaseous non-metal, gaseous non-metal, gaseous non-metal, or we could even say halogen, noble gas. And we get that same cycle, and so the groups are periodic. What do we call this group? You should remember this from physical science. It's 1A or just 1, depending on your numbering scheme. This one labels them, or actually this one being me, has 1, 2, skip a few, 3, 4, 5, 6, 7, 8. But we usually, the two naming schemes we're usually using, the IUPAC suggests this one. 1, 2, 3 is the scandium group. 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 is the boron group. 14, 15, 16, 17, 18 is the noble gases. That's the one that IUPAC suggests. The old way was 1A, 2A, 3B, 4B, 5B, 6B, 7B, 8B, 9B, 10B, 11B, 12B, and then 3A, 4A. It goes back to the A's so that we get the idea of the valence electrons in there a little bit. Another way, by the way, that we can organize these periodically is by valence electrons, by number of valence electrons. How many in this one? 1. This one? 2. Then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. It goes over and over and over again. And these two things are related. The number of valence electron is what determines what group it's in. What is, back to my original question, what is group 1A? We need to name these, and we need to know them, and we need to have them memorized. 1A is the, what do you remember? Do you remember what it's called? The what kind of metals?
The alkaloid metal.
Alkali. Close, Gabe. Alkali metals. 2A? Oh, and by the way, the IUPAC naming system, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, those are all using Arabic numerals like I have up here. The other way, the old way, uses Roman numerals. So 1 being I, A. 2 being double I, A. 3 being I, B. IV, B, etc. Anyway, so 2A would be what? If 1A is the alkali met, no. 2A is this one. Remember, Lily? Yep, alkaline earth metals. And you do need to know these. These are on the test. A large part of your, where the math problems usually are on the test, a large part of that is just identify the name of the group this element is found in. Alkaline earth metals. Three B, let's do 3B. 3B through 12B. This whole block here, 3B through 12B. What do you think? They are transition metals, you're right. Transition metals. And then back to the A's, 3A. I think I've done that wrong. I think it's actually, I wish I had an old, would you run and see in the old periodic table in there if this group up here are 3A or if they're 3B? Because I think these are actually, I think I was wrong. I think this is 3A through 12A are the transition metals. And then 3B will be a different name. But Lily will tell us. Lily, does it? Let me see what your book says. That's really interesting. Let me see what your book says. I think on page 118 we have a pretty good...
Cut the video.
Shh, no, it's okay. No, it's not 118. There's one in the back of the book, though. Yeah, your book just uses the... Let's just use the one that the book uses instead of the old one. So 1 is alkali metals, 2 is alkaline earth metals, and then we'll say 3 through 12. It'll be easier this way anyway. 3 through 12 are the transition metals, and then we'll say 13 is this one here is 13. Well, let me change it on my chart too. 3 through 12. Those are 1 and 2. 13 we usually call the boron group, but it is sometimes, you should know it is sometimes called the icosagens. 14, once again, usually called the carbon group, but we sometimes call it the crystallogens. 15, usually called, somewhat less usually, but usually called the nitrogen group. Sometimes we call it the pnictogens, spelled with a P at the beginning. 16, usually call it the chalcogens. People do still call it the oxygen group, but it's usually called the chalcogens. 17, almost exclusively called the halogens, and 18, exclusively called the noble gases. Crystallogens, or crystallogens, yes.
What's 13 again?
Icosagens. Icosagens. What's the suffix or the part of the word here gens mean, do you think? Yeah, Jenny. No, that's a good guess. It has to do with the word generation. It has to do with the word genesis. It has to do with the word generator. All of those things are when something is... No?
Is 14 alkaloids?
14 is crystallogens. So what do those things have in common? Generation, generator, genesis.
Energy.
No?
And is
Great.
15 picopass?
The way they're all related is those are all things that are, they're all describing the making of something. So a generator makes power. A generation is a making of human beings. It is the group of human beings that were made at the same time. And then the book of Genesis is about the creation, the making. And so gens here is, these are things that in, I don't know, kind of an idealized sense, these are elements that make that. And this comes from a time when people were first looking at the elements, or they were discovering elements, and they were seeing the ways that they made up different minerals. So like the halogens made up salts, which in Greek is halos. The chalcogens made up, well, I mean oxygen makes up chalk, which in Greek is chalkos. Pnictogens, I don't know. Crystallogens, the idea was they made up crystals, I guess. Icosagens, I don't know again. But these are what we call, these groups are what we call the representative elements. And so if I were to color in the representative elements on my diagram here with pink, they're the S block and the P block. Not the transition metals, and not the inner transition metals. So we already had a name for 3 through 12 were the transition metals, and then this F block here are we sometimes call them the inner transition metals. Now, you already know the answer to this question, so this will be fun for you. How many valence electrons do the elements in group 1 have? 1. What about the elements in group 14? How many valence electrons? 4. What about in group 17? 7. You already know how to use the periodic table to find valence electrons. So we also know that valence electrons are what give the chemical properties to that substance, and so, or sorry, to that element. Therefore, if we have all the elements in group 1 have 1 valence electron, and the number of valence electrons is what contributes, or the main contributor to the chemical properties, what can we expect to be true about all the elements in group 1? They must have similar properties, yeah. Yeah, so these all have, group 1 all have similar properties, group 2 all have similar properties. We sometimes even call those groups families because they have similar properties. If, as I have mentioned before as kind of a joke, almost every person in this room, I have taught one of your siblings really this exact same chapter, and it's amazing to me to see the similarities between you. And you're not identical, right? Sodium and potassium are not identical, but they're similar. They have similar properties. Sodium and potassium, if there's time left today, we'll go blow them both up, and we'll see that they are similar. Those both react with water explosively in a way that other things don't. Like you probably know from experience that if you put a dry erase marker in some water, it just kind of sits there. If you put your body in some water, it just kind of sits there. But if you put a lump of sodium metal in water, it explodes. So that's a very interesting chemical property. Yeah, we're going to today. That's a very interesting chemical property that these things share. They don't do it in the exact same way as we'll see in the lab, but they share that kind of unusual property. The same thing with the noble gases. None of these are chemically reactive. They're chemical properties that they don't react. Right? What's the safest way to ski? Don't ski. They just their chemical properties is that they don't have a chemical property. They don't react. But they all do that, and that's very unusual. That's an unusual chemical property for things to have, but they all have that. That's why they're in a family together. That's why we group them together. Yes?
So, sodium chloride is table salt.
Yes.
So is the reason that table salt doesn't react explosively with water because it has that extra...
Yep, we'll talk about it because the question was, how come table salt, which is made of sodium chloride, does not react in the same way that sodium does? And we'll talk about that actually in the next chapter, in chapter 7. But basically, the reactivity that causes it to react in that way with water is used up effectively. It's already reacted with the chlorine to make a new compound, sodium chloride. You should know also about these trends. We have the idea of atomic radius. So in general, as we go down a group, let's say this, how would we expect the size of an atom to change? Like if we compare hydrogen to lithium, which one do you expect to have a larger atom? Lithium. Lithium, let's say it has that big, this little baby. What about the next one down, which is sodium? Bigger. Next one down, potassium? Even bigger. So you're right. The periodic trend going down is increasing atomic radius. Why? It's adding more whats that we learned in the last chapter. Yeah, adding more electrons, adding more electron energy levels.
So you would say increases?
So going down a group, it increases atomic radius. Now, when we go from left to right across a period, what would you expect to have happen with the radius then? Yeah, you'd think it would increase, but it doesn't. It doesn't add a new energy level, right? We know that it doesn't do that from our experience with the electron configuration. It does not add a new energy level, but it does add more electrons. And so now, almost counterintuitively, it decreases inside because there's more electrons and there's more protons. And so there's a stronger electromagnetic attraction. It's pulled in tighter. This actually, as we go across a period from left to right, it decreases in atomic radius. So you're right. Lithium would have a larger atomic radius than hydrogen, but beryllium has a smaller atomic radius than lithium because there are more electrons, but there are not more energy levels, and so it shrinks. It's pulled in tighter to the nucleus. That's atomic radius. I think the last thing we want to talk about is ionization energy, and then we're also going to talk a little bit about the electronegativity. Let's talk about ionization energy first. Ionization energy, you know from your vocab, is what? What's ionization energy?
Defined as the energy required to remove an electron from a gaseous atom.
The energy required to remove an electron, basically. So we say from a gaseous atom because we don't want to worry about what are called intramolecular forces between one atom and another atom of the same kind. But it's how hard it is, basically. The higher the ionization energy, greater ionization energy, is greater energy required to lose an electron. Lily, would you please police these people? How hard would it be for an electron to leave something from group 1?
Hard. Easy. No, it's easy.
Okay, how many valence electrons do all the atoms in group 1 have? One. And because of the octet rule, which was another one of your vocab words, what's the octet rule say? How many does it want to have? I mean, that's kind of a...
The atoms tend to gain when they share electrons in order to acquire a full
Octet means 8. Like octopus, 8 feet. Octomom has 8 kids. What's another octo word? An octagon has 8 sides. Octet means 8. It means that atoms are most stable when they have 8 valence electrons. Hydrogen and helium are accepted. But atoms are most stable when they... I'm sorry. It would usually be an ion. Atomic particles are most stable when they have 8 valence electrons. So these have 1. Well, how can they get to 8? There's 2 ways. They can either gain...
Or subtract.
How many would they have to gain to get to 8? 7. Or they could lose... How many?
So high.
Like if it's potassium, how many electrons does it have to lose to have 8? One, just one. If it loses one, it'll be like argon, which is a noble gas, which will make it happy. So, is it easier for it to gain 7 or lose 1? You lose 1. How much, or will it have a large or a small ionization energy?
Larger.
Small. It will take only a very little bit of energy to remove its electron because it doesn't even want that electron. It wants to have a satisfied octet rule. So these have a very small first ionization energy. We call it a first ionization energy. We're talking about losing 1 electron. So generally, first ionization energy, what do you think the trend for that is? As we go from left to right, do you think it gets easier or harder to lose 1 electron? Harder. Yeah, the elements periodically want to lose their electrons less the further away we get. So the ionization energy, first ionization energy, decreases as we go across here. Decreasing first ionization energy. Now what about as we go down? Well, what's different about these? These all still have 1 valence electron, but what's different? What's different about them? Think about the arrangement of electrons if we were to diagram it with the Bohr model with the nucleus in the center and progressive energy levels. What's different about the way the valence electrons are from, let's say, francium, francium compared to hydrogen? They're what? If we were to diagram both hydrogen, which I can just do right now, and francium, well, it's going to have a much bigger nucleus, and how many electrons do I have to draw around it? 87. I'm not going to take the time. But basically, if I had to diagram it, what's going to be different about the valence electrons compared to hydrogen? They are what? Yeah, they're further away. So is that going to have is it going to be harder to get that electron from them or easier? Easier. It's going to be easier because it's further from the nucleus. Remember, the only thing holding the electron to the atom is the electromagnetic force with the nucleus. So the further away it gets, the more energy levels there are, the lower the first ionization energy. So as we go down a group, we have a decreasing first ionization energy. There's also the concept of second ionization energy, how hard it is to lose a second electron. Now think about the first group again. Potassium, how easy is it for it to lose 1 valence electron? Very easy. But now if it were to lose a second electron, how easy is that? Hard, because now it will already, after losing 1, it will already have satisfied its octet rule and no longer wants to lose the electron. So its second ionization energy is going to be extremely high. Very, very, very high. Basically, the second ionization energy is how hard it is to make it into a 2+ ion instead of a 1+ ion. And so that is the highest for group 1, but then starting with group 2, increases going across the board for ionization energy. The last thing we have is electronegativity, which is almost like the opposite of ionization energy. Ionization energy, remember, is how much energy is required to lose an electron. Electronegativity is basically how much an atom, I'm going to just put in quotes, wants an electron. How strongly it attracts other atoms' electrons. Where would we expect this to be the highest? I said, where would we expect that to be the highest? Yeah. So where was our first ionization energy the highest, or where was the first ionization the lowest? Basically, which element wants to lose an electron the most? Try again. Because remember, it increases going down. Ferrinium is not one of them. You mean francium. It is Fr, but that's francium. So francium will have the lowest first ionization energy of any element. So where would we expect to have the highest electronegativity? On the opposite side.
Helium.
Well, yeah, but not these. We kind of forget about these because they don't want to react at all. Fluorine. Fluorine has the highest electronegativity. So electronegativity increases going from left to right, increasing electronegativity. And as we go down, well, once again, they get further, the electrons that would be added get further from the nucleus, and so there's not as strong a pull. It's not pulling for more electrons as strongly, and so this decreases going down, so decreasing electronegativity. Electronegativity uses an arbitrary scale where fluorine has an electronegativity of 4.0 and francium's is 0.7. It's unitless and it's basically arbitrary. It doesn't have any measurable scientific value. It's just given a comparative value to the other ones. Fluorine's is actually 3.98, which is 4.0 with sig figs, but 3.98. And we will do this in chapter 8, I believe. We will do this to determine, we'll use the electronegativity chart to determine how polar a bond is. But for now, it's good enough that you know that electronegativity is how badly it wants another electron, and that fluorine's is the highest and francium's is the lowest. So we have all these different trends in the periodic table. The periodic table is one, I think probably, I've said before, this is a triumph of human organization, because we could just alphabetize them. Lavoisier's original idea when he discovered many, many elements was he just had them listed, like just an up and down list. We could have them organized by atomic mass, as people had done in the past. But the way we have it organized right now, with the starting over of new periods and the energy levels being diagrammed throughout it, is really a triumph of human organization. It's just a beautiful structure when you learn to understand. There's so many, the fact that we can talk, or I can talk, for 37 minutes now about all the different ways we can get trends out of this one organized table is just a marvel of human organization, I think. You have questions about the periodic table? I kind of glanced over the very basic things that I assume you already know, like how is it organized? Like what are the things, in what way do we, it's organized by atomic number. We organize them by the number of what in the nucleus? Protons. Good. So you already know about most of those things. Do you have any questions about the periodic table? There isn't math in this chapter to speak of. The part where your test would have normally had math, you will be drawing electron dot diagrams from the last chapter, which also deal with valence electrons that we talked about today, and you will be telling what group they're in. Okay, let's go blow something up. Bye!